Differential and integral operations 13. Maxwell's equations in vacuum are: curl of electric field is minus del B del T, curl of magnetic field is mu 0 epsilon 0 del E del T, divergence of electric field is 0, divergence of magnetic field is 0. Manipulate these using subscript summation notation to obtain the wave equation in vacuum. Laplacian electric field is mu 0 epsilon 0, second derivative of electric field with respect to time. Alright, so first notice that the wave equation relates two vector fields, magnetic field and electric field, so we need to use the curl equations. So let's start with curl E. So curl of curl E is epsilon ijk in EI hat direction, del xj, and curl E's k component. All right, and this is equal to epsilon ijk. Now I can open up curl E's kth component, del xj, epsilon klm, del em, del xl, in EI hat direction, and this is equal to epsilon ijk. Now klm I'm going to reorder, so let's remember that when I have klm, this is clockwise direction, that's positive direction. klm is the same thing as lmk. So this is epsilon lmk. I want to use the Levi-Civita identity, del xj, del em, del xl in EI hat direction. Now the k index is in the same position, so the Levi-Civita identity tells me Kronecker delta first indices, Kronecker delta IL, Kronecker delta second indices, JM, minus Kronecker delta inner indices, JL, and outer indices, IM. Then I have del xj, del em, del xl in EI hat direction. And Kronecker delta tells me that I have to set j equals m and l equals I. So setting j equals m here, I will have del xm, del em, del xl, but L is set equal to I, so del xi EI hat. And then I have minus. Now the second term says J must be equal to L, so del xl, del EI, del xl, because M should be set equal to I, according to this Kronecker delta, EI hat. All right. Now here I have del xi of del em, del xm in EI hat direction. So let me rewrite it here. This is changing the order of the derivatives, doesn't matter. Del xi, EI hat. Then I have del em, del xm, which is the divergence of the electric field. Then for the second term, I have the second derivative of the electric field with respect to XL, so del square del XL square EI in EI hat direction. Now once again, this is just the divergence and this is the gradient operator. So gradient of divergence of the electric field minus, this is the Laplacian operator, del square Laplacian operator applied to electric field, and that is just equal to minus del square electric field, since one of the Maxwell equations says divergence of the electric field must be 0. Therefore, I have curl of the electric field equals, now on the other hand, I have a curl of electric field is minus del t curl of B. So because the curl will be operated on the magnetic field B, and curl B is equal to mu 0 epsilon 0 del E del T according to this Maxwell equation. So that is minus d dt mu 0 epsilon 0 del E del T, which is minus mu 0 epsilon 0 second derivative of the electric field with respect to time. So what do we obtain? So we obtain the wave equation in vacuum minus Laplacian electric field is equal to minus mu 0 epsilon 0 second derivative of the electric field with respect to time, or the minus signs cancel. I can rewrite this result as the Laplacian of the electric field is mu 0 epsilon 0 second derivative of the electric field with respect to time. So that gives me the wave equation in vacuum. That's what we were supposed to prove. Okay, so this question is about Maxwell's equations in vacuum. Curl E is minus dB dt. Curl B is mu 0 epsilon 0 del E del T. Divergence of electric field and magnetic field are 0 in vacuum. So this implies Laplacian of the electric field is mu 0 epsilon 0 second derivative of electric field with respect to time. I take the curl of this equation. Curl of E is minus d dt curl of B. So for curl of B, I substitute mu 0 epsilon 0 dE dt. That's what I did at the end here. That gives me minus mu 0 epsilon 0 second derivative of electric field with respect to time. As for curl of E, I have to use an identity. And to figure out what this is, I use subscript summation notation. This is epsilon ijk ei hat del xj of k component of curl E. K component of curl E is epsilon klm. It would be in ek hat direction, but it's k component, so no ek hat. Del xl applied to em. So KLM can be reordered as LMK, and using the Kronecker delta conversion from epsilon product of two Levi-Civita symbols with the common index in the same location, Kronecker delta firsts, seconds minus inners, outers applied to this. I have J must be set equal to M. M remains, and L must be set equal to I, so that's the first term. Then J must be set equal to L, and M must be set equal to I. This is second derivative with respect to XL of the electric field. And this is, because I can change the order of the derivatives here, gradient of the divergence of the electric field. And divergence of electric field is zero. That's one of the Maxwell equations. So that means this term is zero. So minus Laplacian electric field is minus mu 0 epsilon 0 del square E del t square, minus signs cancel, and I've obtained the final equation, wave equation in vacuum.